Thank you. Thanks all of you for joining us. I'm Tudor. I'm going to be just going fairly quickly through mainly the first part of the presentation. I'm going to introduce myself. I'm going to introduce the Rockset, and then I'll hand it over to Karen, and I'll stick around for the questions and answers section at the end. So as I said, I'm Tudor. We are Rockset. Yes, Rockset is a real-time analytics database in the cloud. We connect to data streams. We are able to ingest data from a variety of sources. Some of those are data streams like Kafka or Kinesis. Some are OLTP databases. Some are data lakes like S3 or GCP. Yeah, we are ingesting the data, and then we provide full feature SQL support on it for analytics. The data does not need to conform to a very strict schema. We are pretty much schemaless. So if, for example, if some field is missing from some documents or has different types among different documents, that is something that we can do. We index everything 3 times, and that's going to be on the very next slide. Essentially, we have a column store, which makes us similar to warehouses in that we are optimized for long scans. For large scans, we have a row store, which I'll talk about in a second, and we have a search index, which allows us to be efficient for high selectivity queries, like where product ID equals something. And of course, the row store is used as in traditional databases to retrieve entire documents that have met the search query. I believe that's basically all I have to say. I will be around for the Q&A. Karen is going to take it over from here. Karen did most of the implementation for Rollups, so she's absolutely the best person to speak.
Awesome. Thank you so much, Tudor, for the intro. So I'm Karen, and I'm going to be talking a bit more about Rollups. So we're going to start off with why did we build Rollups in the first place? So Rollups are a way for you to pre-aggregate and transform your data at ingest time. And so how it works is that when you create a collection in Rockset, if you want to use Rollups, what you need to do is specify one single SQL query, which is the Rollup query. And you can think of the Rollup query as a standing query that runs continuously on your incoming data and transforms it as the data streams in. So most likely your Rollup SQL query is going to look something like what we have here. So you're going to be grouping by a couple of dimensions and then running some aggregation functions on your other fields. And then the from input part of this query is standard to all Rollup queries. It's basically just representing the input data stream. So the reason why we built Rollups is to make it more efficient to perform analytics on streaming data. So you can imagine that there could be times where you have a lot of data streaming in, and so it's really expensive to index and store the entire raw data set. And in other cases, maybe you already know that you only want to perform analytics on an aggregated set of your data. And so why not do that at ingest time? And so if you do that in ingest time with Rollups, the benefits you get are that you will reduce the storage size. And then you also get improved query performance because you've essentially pre-computed the fields that you care about. So let's look at an example of how you could use Rollups. So in this case, let our data source be a network of cameras that detects cats and dogs. So periodically, each of these cameras is going to emit an event of the following form. Your event's going to contain a timestamp, a location, and the number of cats and dogs seen. So this data stream is streaming in, and you want to perform some analytics on this. So let's use the following Rollup query as an example. Looking at it from top down, we can see that first what we're doing here is we're massaging our timestamp field a little bit and putting in an output field called event time. We also select location because we're going to be grouping by event time and location. And then we compute a bunch of metrics. So we take the sum of the cats seen, we do the animal count high watermark using the max aggregation function. And then at the very end, we have my crazy metric, which is a pretty contrived educational example of how complex your Rollup queries can get. So here we're combining the results of 3 aggregate functions, count star, average, and approx distinct using some mathematical functions. So here we can see what our Rollup query is actually going to do to our raw data stream. So in the source data preview section, that's the raw data stream. And then the transformed preview is going to show you what happens to your data after it's passes through the Rollup query. So here we can see we just have one input row of data that's going to map to one aggregation group. And so we end up with one output row. Things get a little bit more interesting when our second row of data appears. And in this case, the second row of data maps to the same aggregation group as the first one. And so what the Rollup query is going to do is actually merge and aggregate these together. And of course, your metrics get updated appropriately. Now the row of data comes in. This time it's going to a different aggregation group because the location Los Angeles is different. And so now we have two output rows in our Rollup collection. Another row belonging to the second aggregation group. And so we still have two output rows of data, but our aggregation functions, their values have been updated. And then finally, we get one more row of data, and this one belongs to a third aggregation group because the time and our granularity is different. And so at the very end, our Rollup collection is going to contain 3 rows of data. So now let's look at some of the design principles we used when creating Rollups. So there are 3 main design decisions, and looking at them one by one, the first one is that we wanted to keep a SQL interface for Rollups to make it easier for users to start using Rollups. So you don't need to learn any other language to define your Rollups. You can just continue using SQL. The second point is that we wanted to keep the real-time nature of your data, even when you use Rollups. And so the traditional ahead of time aggregation approach means that you actually don't have access to your data until the end of the aggregation interval, because you need to look at all of the data to know how to merge it correctly. Rockset takes a different approach where we actually do allow updates to aggregation groups. And this allows you to query your Rollup collection in real time and see the results as the aggregations are happening. So this brings us to our third point of handling out of order arrivals. And because we said that we do allow updates to aggregation groups, handling out of order arrivals just works. So this information on this slide is a bit redundant, but basically we're just going to reiterate that with the real-time aggregation that Rockset provides, you're able to update your aggregation groups, which allows you to have your data be available in real time, and we can trivially handle out of order arrivals. So we all know that there's no such thing as a free lunch. And so the trade-off of real-time aggregations is that it requires a more complex implementation under the hood. One part of this complexity is that we must store the partial states of aggregations. So the partial state of an aggregation is the state you need to maintain to compute the final value of your aggregation function. And it also has the property that it can be updated incrementally. So here we have 2 aggregation functions as our examples, average and max. So looking at average first, we can see that the partial state here is actually 2 values, the sum and the count. And then the final value or final state is going to be the average. And then with max, the partial state is the max value seen so far, and the final state is the exact same. So an interesting point to note here is that the partial state of an aggregate function may or may not be the same as its final state. Another change to the design with Rollups is actually how we index these Rollup collections. So like Tudor was saying before, we have converged indexing, which means that we store all of the data in 3 different indexes. So the row store and column store stay the same, and the only change is in the search index. So with Rollups in the search index, we index all fields except for the ones where the aggregate function value has a different partial state from the final state. And the reason for this is that when you do a lookup in the search index, you're going to be using the final value of the aggregate function. And if the partial state that's stored is not the same as the final state, you won't really be able to perform that lookup. And so there's no point in storing it in the index. Next, let's look at the implementation and some of the challenges we face there. So first, I'm going to be talking about how we decompose the Rollup SQL query. So I've mentioned that to use Rollups, you specify one single SQL query, which is the Rollup query. And so it's interesting that conceptually, this is actually 2 separate queries, the ingest query, which contains a logic that happens at ingest time, and then the route query, which contains a logic that happens at query time. At ingest time, what we do is compute the partial state of aggregate functions. And we also compute simple expressions, which in our context just means expressions that don't involve aggregate functions. In addition, we'll also execute the where clause to filter out unwanted input data rows. And of course, we run the group by clause to merge aggregate groups so that multiple input rows that go to the same aggregation group will just form one output row. Then at query time, we need to finalize aggregate functions, where finalize is the process of converting the partial state of an aggregate function to the final state. So, for average, this is the time where we actually compute the division of the sum and the count. We also need to compute complex expressions, which are expressions that do involve aggregate functions. And finally, the having clause also needs to be executed at query time because it requires performing a filter on an aggregate function value. So going back to our example from before, let's look at how we can decompose this into the ingest query and the wrap query. So everything that's highlighted will be executed at ingest time as part of the ingest query. So we can see that we're able to compute our event time field because it doesn't rely on any aggregate function values. Similarly, the location field just passes through directly from the input. And then we have to compute the partial states of our aggregate functions. And at the very end, of course, the group by is going to merge input documents that map to the same aggregation group. To make our example a little more concrete, here on the left, we have some raw input documents. And then on the right, we can see how they get transformed by the ingest query. And these documents are going to contain event time in the location fields, which will be executed. And then it's also going to have the partial states of our aggregate functions. Next, the wrap query shows us what's going to run at query time. And for us, we only need to finalize two aggregate functions, average and approx distinct. And then we're going to finally compute my crazy metric. And so on the left, we have the documents we were just looking at that were transformed by the ingest query, and then they'll pass through and get transformed by the wrap query. And so the documents transformed by the wrap query are the final user visible documents that you see when you query your Rollup collection. So event time and location, which we already had before, stay the same. And then we'll see that we actually compute the final values of all of our metrics, which are cat count, animal count high watermark, and my crazy metric. Next, we'll talk about how we execute SQL at ingest time, or in other words, how do we actually run the ingest query part of the Rollup query. So first, taking a step back, let's look at the write path in Rockset without Rollups. So customer data is going to be living in a variety of data sources, and it's going to make its way into Rockset through the Tailor service. Tailor service contains the logic needed to extract data from these different data sources. And it's going to write the raw input documents into a distributed log, which serves as our write-ahead log. Then a different service called the leaf is going to tail documents from the distributed log and index and store them in RocksDB. So the leaf service maintains the RocksDB instance that's needed for both serving writes as well as reads at query time. With Rollups, the picture gets a little bit more complicated. And the difference is that now we've inserted a new service called the aggregator, which sits in between the tailor and the distributed log. So of course, the tailor has the raw input documents, and it's actually now going to pass them to the aggregator. The aggregator will run the ingest query on the data and return the transformed documents to the tailor. And then the tailor will write those transformed documents to the distributed log, where the leaves will pick that up and index them in RocksDB. So let's zoom in a bit to the RPC between the tailor and aggregator services. So on the left, we have the raw documents that get sent from the tailor to the aggregator. We have a new Rollup query example just for the sake of space, so everything fits on one slide. And here we're just going to be grouping by location and then computing the partial state of the average function. And so you can see in the transform documents that they've been grouped by location, and we have the partial state of the average. And then these transform documents get sent back from the aggregator to the tailor. So here's our same diagram again. Now it's been annotated with a few diagrams. So the diagrams on the aggregator service show that the raw input data could get merged when we run the ingest query, and multiple rows of input data map to the same aggregation group. And then you'll also see that on the leaf, there's a diagram. And what this is saying is, it's kind of a spoiler for the next section, but we actually do need to do some merging on leaves as well in some cases. And the reason why we have to do this is that, to keep the data real time, the leaf is going to be able to serve reads for its existing aggregated Rollup state, But if some document comes later out of order, we still need to be able to update the state on the leaf appropriately. So yeah, we're going to talk about how we handle these out of order arrivals. And like we were just saying, the leaf service needs to be able to update existing aggregation groups. So let's say the state on our leaf is just these two documents. We're grouping by location. And then we tail a new document from the distributed log on the leaf. And this document belongs to the same aggregation group as one of the existing ones because location San Francisco is the same. And so the leaf needs to be able to update that aggregation group. So the way we handle updates to an existing aggregation group on the leaf takes advantage of an existing principle in Rockset, which is the _ID special field. The _ID special field is the primary key in a Rockset collection, and every single document in every Rockset collection has the _ID field. And because it's the primary key, we give you upsert write semantics based on the value of that field. And so if you have a write that's going to the same document because it has the same _ID value, then we'll actually update your existing document. For rollups, what we do is we set the value of the _ID field to the 128-bit hash of the grouping dimensions. And by doing this, we establish the relationship that one rollup document represents exactly one aggregation group. So going back to our favorite example here, we see that we're grouping by event time and location. And so what this means is that every document in this rollup collection is going to have an _ID field with the value of the 128-bit hash of the event time and location. And so when you get updates to the same aggregation group, you'll know that they're actually going to the same rollup document because the _ID value is the same. And so we take advantage of the existing upsert semantics. And the way we actually update your existing rollup document is just using a read, modify, write approach. And I'm going to note here that the only values we need to update in your rollup document are the aggregation function partial states. And that's because the only other fields that could exist in your rollup document are the grouping dimensions. And by definition, those will not change. So what we do is we load the aggregation function partial state into memory from RocksDB. We update the partial state in memory, and then finally we write that back to RocksDB. So the logic that's used for merging aggregation partial states here is actually the same logic we use in distributed aggregations at query time. So going back to our average and max examples, for average, what we do is we take the sum of the sum and count fields independently to merge the partial states. And then for max, we just take the max of the two input values to get the final merge state. And so the logic for merging partial states for different aggregation functions will differ and needs to be defined independently. Next, let's talk about write semantics. So by default, Rockset supports at least once write semantics. And if all of your updates are idempotent, then that's totally fine. It doesn't matter if a write gets applied multiple times, that your final state is always going to be the same. On the other hand, rollups need exactly once write semantics because if a write gets applied multiple times, you could end up with double counting issues and your aggregate function values will be incorrect. Our implementation of exactly once write semantics comes from our mental model of how streaming data sources work. And so our mental model is that we have writes arriving in n independent streams, and within a given stream, the writes are ordered. So for our exactly once write semantics implementation, we assign a unique update ID identifier to every single write. The update ID is composed of two separate fields. The first is the shard ID. So which shard does this write belong to? And then we have the sequence number because we know that the writes are ordered within the stream and this sequence number is monotonically increasing. So in practice, the value of the shard ID is going to be your Kafka partition or Kinesis shard. And then the sequence number is going to be the offset. So now that every single write has an update ID, the leave service will enforce exactly once write semantics by rejecting writes for a given shard that have a sequence number that is less than or equal to the highest sequence number we've seen so far for that shard. And because if we see that the sequence number is lower than the highest that we've seen so far, we know that that write has already been applied, and so we don't want to apply it again. The metadata for the mapping from shard to highest sequence number seen is persisted in RocksDB. And we can prune this metadata on a per shard basis whenever we know that a shard is never going to get any more updates. So that was a lot of information. Let's just summarize the implementation again. So looking at the write path first, the tailors will send the raw input documents to the aggregators, where the aggregator services run the ingest query and return transformed documents. Then the tailor will write these transformed documents to the distributed log so the leaves can tail and index them. And then, of course, the leaf needs to be able to update Rollup documents as needed. And throughout this whole process, we need to make sure that writes are processed exactly once to avoid any double counting issues. Then on the read path, you can think of querying a Rollup collection like querying a view, where the wrap query is the view query. And what the wrap query does is finishes the computation of the Rollup query using the values pre-computed in just time. So we're going to finalize all of our aggregate functions. For average, we'll compute the sum divided by the count, and we'll compute all of our complex metrics. And then just an interesting implementation detail is that we've said that conceptually querying a Rollup collection is like querying a view, but actually the implementation for the views and querying a Rollup collection is the same. And if you want to do it yourself, all you need to do is create an account at rockset.com and try out SQL Rollups on your streaming data. Cool, so that's all the content we have. And I think now it's time for the Q&A. Should we switch over to spatial chat or just stay here?
It does not appear like there are any questions in the Discord right now. So I want to thank you. There's some really cool stuff you guys are working on. And then we could have everybody switch over to the spatial chat and have Q&A there.
Okay, sounds good. I guess we'll see you all there. Thank you.